Hello, pre-AP Physics! This is the last video. So today, touchy-feely, I came to you dressed as just Mr. Foster in the iconic dinosaur t-shirt or button-up shirt, whatever. Please ignore how long my hair is and how it makes my big head look bigger than it already is. Um, and also, no backdrop today either, because well, I could say because we're taking it back to the roots, the OG style with no backdrop. But the truth is that my wife used part of the things that I used to set it up to pack things up and put them in a storage unit. So I don't have the set anymore because it was a couple of boxes that I would stack over here and like hang up a rod, and those are in a storage unit now. So. That's the real reason why there's no backdrop, and I'm remembering why because that window is really, really bright. But details, details. It's the last video. Let's knock this out. So, last video, our topic. We talked about series circuits yesterday, so we're rounding out our circuits talk. There's more to talk about, but this will get your bases covered. Is just talking about parallel circuits. So parallel circuits, remember, look like this. There's the two different branches that have different resistors on them, and we're going to talk about why you would do that. Like, what's the advantage of having resistors in parallel? Because there's a really big advantage. In fact, everything in your house, or at least most things in your house, are wired in parallel for this very reason that we'll see in a moment. We're going to pull out the simulation, but I want to pull out the whiteboard first to show you some things. So, whiteboard first. Simulation second. So I'm going to draw a little parallel circuit right here with the battery, resistor number 1. If you hear some stuff outside, it's because they are doing construction on the unit next to us and like the AC units right here, so they're messing with the HVAC and stuff. So I hope there's no drilling into the wall while we're doing this because that's loud. So this right here is my parallel circuit. Now, big difference here. Important thing to notice is how the battery and the circuits are wired up and how that affects the voltage. So we're going to just pretend this is our 10 volt battery like we've been assuming, right? So that means that this side is 10 and that this side is 0. 0 volts. Forgot the V. All right. So remember, what we said is that we assume that there's no voltage drop in wires. The voltage drop takes place across resistors, right? So that means that we've got 10 volts all the way through here to both resistors, right? So it's 10 volts here and it's 10 volts here, right? Same goes for the other side, right? There's no voltage drop here and it's 0 here, so that means it's 0 all the way through here and all the way through here. So it's 0 on this side, 0 volts here, 0 on this side, 0 volts here. So notice that each of these resistors has a voltage drop of 10 volts across it, right? 10 volts for both of them because of the way they were wired up. Remember, if we had them in series, I'll draw that real quick actually to compare. So resistor 1, resistor 2. So when they're in series, right, if this side is 10 volts and this side is 0 volts, then this side of the resistors is 0 volts. This side of this resistor is 10 volts, right? So in this case, the series circuits, both of these resistors together overall see a drop of 10 volts. So one might be 5 and the other might be 5. You might have a 6 and 4 situation, but they add up to 10 volt drop, right? Whereas in this case, both of them see a full 10 volt drop. And this is really important when it comes to things in your house, because remember, I said that your light bulbs, for example, the brightness of the light bulb depends on the voltage drop across the light bulb. So let's flip on over to the circuit simulation I've got right here. Here we are. I've got it wired up already in a parallel circuit. Ignore this a little bit down here. It's gonna help me turn it into a series circuit later. So I've got it wired up in parallel. I've just made this one 10 volts, this one 10 ohms, this one 10 ohms, and this one down here is also 10 ohms, so it's all consistent. Now, I've got it in this view because remember, this is the view that we can see the brightness of the bulbs in it, and look how bright these are, nice and bright, right? I can even take the voltmeter and prove to you that, see here, the battery is 10 volts, right? this light bulb here is 10 volts, and this light bulb here is also 10 volts, right? So that matches up with the drawing that I did before, right? So I'll put that away. And look how bright these are. So this is parallel wired up. Now I'm going to take the exact same light bulbs, snip these circuits real quick, and I'm going to wire it up. I'll move this over. I'm going to wire it up in a series circuit, and we'll see the difference. That was why I have this over here. All right, so now these light bulbs are wired up in series, and notice how much darker the lights are, right? This is a realistic representation of what's going on with the light bulbs. See how much darker these are compared to they were before. This is still a 10 volt battery. These are still 10 ohm light bulbs. So the only thing that's changed here is the voltage drop across, well, the current's changed technically too, but the important thing here is that the voltage drop across each of these light bulbs changed, right? If I pull the voltmeter, this one should have a drop of 5 volts. Yep. And since they're the same, they each have half of the drop. And this one should be 5 volts also, right? So our voltage drop across each of these light bulbs has been halved. And look how much that's affected the brightness of the light bulb, right? So this is exactly why we connect things in parallel in our, I'll put this away, in our houses, is because they, there we go, as if you plug up more and more light bulbs into your circuit, if it's a series circuit, they would get darker and darker and darker, or you would have to use a lot higher voltage of power, which is dangerous. The higher voltage is the more dangerous it is to humans. So we wire things in our houses in parallel so that all of the things experience the same voltage, and we don't have to use some massive battery, or we don't have to limit the number of things we plug into the wall. So that's the advantage of parallel wiring. It's really cool. Now we can actually solve problems with our parallel wiring, but the one thing we're missing is how to make equivalent resistance, right? So erase what I have right here real quick. All right, so how do we calculate equivalent resistance for a parallel circuit? So be warned, this might look a little bit scary, but I promise it works out just fine. Mostly because of the way that we're solving the problems. So for a parallel circuit, the equivalent resistance, it's actually 1 over Req is equal to, if I've got resistors R1, R2, R3, right? We've seen that set up. I don't feel like I need to draw one here. It's 1 over R1 plus 1 over R2 plus 1 over R3, and so on, depending on how many things you have in parallel, right? So this is how you calculate it. You take 1 over the resistances, add them together, and then notice that you have to flip that, right? Because this is 1 over the equivalent resistance. So you add these up, and then you flip that. I'll show you examples. It's straightforward. Calculators have like an inverse option that you can do, or you just say 1 divided by answer, or whatever. So let's take a look at our first example. Number 1, we have a little circuit diagram. I'll draw it up here. The parallel circuit, positive, negative, resistor here, resistor here. Okay, so we have a 12 volt battery. This resistor is 2 ohms. This resistor is 3 ohms. Great. Part A asks us about the equivalent resistance of the circuit, or of the two resistors is what it says. So we just calculate equivalent resistance like I just showed you, right? So our equivalent resistance, A, first of all, our equivalent resistance, 1 over Req, is equal to 1 over, I'll write it in variable form, I guess, first, right? R1 plus R2, just 2 resistors here. So our R1 is 2 ohms. R2, we'll say, is the 3 ohms. So we have to add fractions. If you have a calculator, great. If you don't remember how to add fractions and don't have a calculator, have fun. It's not that hard, right? You just find a common denominator, which this one is 6, right? So then you would multiply by 3, whatever, so that this 1/2 is 3/6, and then 1/3 is 2/6, so 3/6 plus 2/6 is 5/6. So our 1 over Req is equal to 5/6, right? But we need to flip that, so that we flip this. So you just flip both sides so that our Req is equal to 6/5 ohms, aka that's 1.2 ohms if you're doing it in decimal. So 1.2 ohms, 6/5 ohms, that's our equivalent resistance for the circuit. I can give pretty numbers, I just didn't have pretty numbers to give on this one. If I give you problems, they'll probably be prettier numbers, like on your exit ticket. So that's all for part A, our equivalent resistance. Part B next. B. What is the current flowing through the battery? So now we have, I made the distinction here through the battery. I'll talk about that in a second after we solve this. But basically, it's what is the current flowing using that equivalent resistance, right? Because if we've got our equivalent resistance here, it looks like this, just this circuit, 12 volts, 1.2 ohms, right? So this is our equivalent circuit here with the equivalent resistance, and we can find the current, right, using V equals I, our Ohm's law. So V equals I, I'll even specify Req. Our voltage is 12 volts. We're looking for I. Equivalent resistance is 1.2 ohms. So just divide by 1.2, right? 12 divided by 1.2 is 10 amps. Underline. All right, so that's our current flowing through the battery. So why do I say flowing through the battery and not flowing through the circuit? So here's another big difference between parallel and series circuits. Notice that you've got these little branch offs right here, right? This is what's called a junction, where there's a branch of different circuit elements. So I specified that this is the current flowing through the battery. That means that it's the current flowing like in this branch right here, right? This is 10 amps right here. Now, if we're going with our water metaphor, right? When you hit like a fork in a river, some of the water flows one way and some of it flows another way, right? And our flowing water, that's our example of current, right? So when our current hits this point, some of it goes to the 2 ohm resistor and some of the current flows to the 3 ohm resistor, right? You have some of it goes one way and some of it goes the other way, right? This is a law we would have gotten into if we had more time. It's Kirchhoff's junction rule, that the current that goes in would split. So technically, the current through here should add, and the current through the 2 ohm and the 3 ohm resistor should add equal to 10 because all of the current is splitting. But that's a rule we're not really getting into because we didn't have time because of the cutoff of the year, whatever. That's fine. So this 10 amps is the current through the resistor. But part C asks us what is the current flowing through each individual resistor, or the 10 amps is flowing through the battery, I think is what I meant to say. So part C asks us about the current flowing through each of the resistors. Now, there's a few ways that you can do this. Like I said, this is the more complicated way, but we won't have to solve any of the problems we'll see this way, but I wanted to throw this out there and then we'll come back to it. So, like I said, all of that 10 amps splits off, and one goes one way, one goes the other way, but it's 10 amps total that splits off, right? None of that current goes anywhere, it just some goes one way, some goes the other way. Now, the current that splits is proportional to the resistances. Now, if you ever heard like the path of least resistance, right, is the path that you want to go down. People don't naturally want to be resisted in a path, and current as well as water is the same, right? So whichever way is easier for the current to go, more current will go that way. So we would expect that the 2 ohm resistor would have more current flowing through it than the 3 ohm resistor, right? The current wants to find an easy way back to the other end of the battery. So more of it's going to be flowing down to the 2, or through the 2, than the 3. So what you can do with this setup is the current it's actually proportional to the difference between them. So you could set up a proportion and solve that way. Or we can do this the easier way, which we have the voltage across each of them, right? It's 12 volts across each of them. We have the resistances, so we can find the current as well. That's a shorter way to do that. But I'll tie us back so that we can double check our answers using the other method. But for now, we'll just do part C using Ohm's law, V equals IR. Right. So we'll start with the 2 ohm resistor first. Our voltage across V equals IR. Our voltage across them is 12. Our resistance is 2. So 12 volts is equal to I times 2 ohms. Divide by 2, current is equal to 6 amps. Easy maths here, right? The second part is using the 3 ohm, still using V equals IR. Our voltage across it is still 12. They're wired in parallel, right? 12 volts is equal to I times 3 ohms. Divide by 3, current is equal to 4 amps. Boom. You can see here, I did not lie to you, right? These add up to 10 amps. So 10 amps goes into the junction, 10 amps comes out of the junction, 6 if it goes one way, 4 it goes another way. And the 2 ohm one has the larger value flowing through it, right? 6 amps, bigger than 4 amps, so more current's going through the 2 ohm. That checks out with our knowledge. And it's also proportional if you did the proportion, right? So 6 divided by 4 is 3 over 2. Our relationship is 3 and 2 for the resistors. Don't worry about that, though, because we won't be solving any problems that you need to do that with. But we can double check at least that we got the bigger value for the smaller resistor, and we did, so good on us. Boom, that's all you do, though. Pretty straightforward setup for parallel circuits. It would be the same sort of process for all of these. Your big detail is just to remember that the voltage is consistent across each of these branches because of what we talked about. So yeah, that's all for number 1. And really, this is all that I'll expect you to do with parallel circuits. But I wanted to show you a circuit with both parallel and series resistors in it, in order just to show you how you would do that if you see those in some sort of future class that you were in. But obviously, that wouldn't be in this class. So, number 2, just a little extra interesting challenge problem. Plus, you'll see the series and parallel practices again. So this is what, let me pull it up, I guess. Yeah, there it is. So this is what that circuit looks like. Plus minus. There's 2 resistors here on this first branch, 1, 2. And then we've got another one here on this branch. Resistors, or circuits, can start looking really crazy, and they become a really cool puzzle. But unfortunately, we don't have time to look at that. I'm so sorry, sad. They can be cool. People really like them, like I said. 2 ohms, 6 ohms, and 4 ohms. But sorry, we won't get to see that. All right. So our first problem, part A, as with the previous problems, just asks us what is the equivalent resistance of the circuit. But our issue here, right, is that we have a parallel part in this section and a series part in this section and a parallel component to that, right? So how in the heck do we tackle this? Well, so the first thing that you should do when you see multiples like this is you should be on the lookout for parts that are in the same branch, that are isolated. And in this case, we have these 2 that are very obviously in series with each other, right? They're in series first. And then these 2 are in parallel with the larger 4 ohm one, right? So what we can do is we can combine the 2 and the 6 ohm and make that equivalent, and then that equivalent one is in parallel with the 4 ohm, right? You see how I could combine these? I could take these out of the series and put just one, and then that one is in parallel with the 4. So that's the route that we're going to take. Since these 2 are in series on their own, we can simplify them first. Now, I feel like I don't need to write all of this out. But the idea here, right, is that series ones, you just add the resistances. So 6 plus 2, this could be replaced by a singular 8 ohm resistor. So I guess I'll go ahead and draw that out, right? So now we're left with this. If you don't feel like you need to do this in the future, you don't have to. Of course, I guess that's me speaking for another teacher in your future. if you retake physics in college or something. 10 volts. All right, so we're left with this 10 volts, 8 volts, or 8 ohms, 4 ohms, right? Now we have a parallel circuit like we just saw, so we can solve for equivalent resistance. Now, this will be our final one, so I'll write that out up here, right? For part A. 1 over equivalent resistance is equal to 1 over, I won't write this in variable form because we've seen the formula twice now. 8 ohms plus, or 1 over 8 ohms plus 1 over 4 ohms. 1/8, 1/4, right? Our common denominator is 8. So this is 1/8 plus 2/8. So that is 3/8. And then we just flip that, right? So our equivalent resistance is equal to 8/3 ohms. That's 2 and 2 2/3. So 2.67 if you're doing that. I guess I'll write that out here. 2.67 ohms if you're doing that with a calculator or something. All right. Part B says, what is the current flowing through the battery? Remember, that's the whole circuit current, so using our equivalent resistance, right? B is just V equals I Req. Our voltage is 10 volts. Current times our resistance, which is 2.67, I guess. I'll use that. 10 divided by 8/3, right? It's 38ths, unless I did bad maths. Divided by 8/3, yeah, 38ths, aka 15/4, which is 3.75. 3.75 amps. Sorry, no pretty. Well, these are fine numbers, right? That's just 3/4. I didn't give you like really ugly numbers on this one. Again, your other answers will be prettier probably. All right, so that's our current, 3.75 amps. That's our answer to part B. Part C says, what is the current flowing through the 4 ohm resistor? Now, again, this is where you might have like a complicated setup where this is where the complicated setup would be more complicated. Where the 3.75 amps splits off. Some of it goes into the series branch, some of it goes into the 4 ohm branch. And it would be like you wouldn't want to set up that proportion. It's much easier just to do our voltage row, right? So since these are in parallel here, our 4 ohm resistor has a 10 volt drop across it, right? 10 volts here, 0 volts here, right? So our voltage across the 4 ohm resistor is 10 volts. See, we can just do Ohm's law to solve for current. V equals IR. Our voltage across the 4 ohm resistor is 10 volts. We're looking for current. Resistance is 4 ohms. So 10 divided by 4, that's 2 and 2.5, right? 2.5. 2.5 amps. If you get a larger number than 3.75 there, you've done something wrong, right? Because it has to be less than, it has to be a portion of that 3.75 amps. So that's a good double check there. Fortunately, we got a number that's smaller, which checks out, right? Great. Last but not least, we have part D, which says, what is the voltage across the 6 ohm resistor, right? Part D, what is the voltage across the 6 ohm resistor? Now, looking back at our diagram here, right, we know that both of these overall experience, the series branch experiences overall a 10 volt drop, right? Because it's 10 volts on this side and 0 volts on this side, right? So we know that the 2 and the 6 overall experience a 10 volt drop, and we're trying to figure out how much just the 6 experiences. So the voltage drop, we didn't talk about this as much in the series one, but the voltage drop is also it's also proportional to the relative resistances. So you could do that, or you could use this equivalent circuit we made right here to find current, use current and the resistance to find voltage. So I'm going to do the current one because that's a little more concrete, and I don't have to pull in proportions or something if you don't like those for math or something. Although I guess there's lots of math here anyway, so sorry. But yeah, what we're going to do is I'm going to use this circuit that we drew right here. So we have an equivalent resistance of this 2 and this 6 of 8 ohms, right? And we know that if this were an 8 ohm resistor, that due to this drawing here, we have it in parallel, we have a 10 voltage drop across this equivalent 8 ohm resistor. So we can figure out the current going through this branch with the 8 ohm, which would be the same current that goes through the 2 and the 6, right? That doesn't change the current. The current's the same regardless of if it's the 1 resistor or if it's the equivalent resistor. It's kind of the idea that we can replace the resistors with an equivalent resistor that would cause the same current to go through. So the current going through here is the same as the current going through here. So we can use, I'm going to move this over a little bit. We can use Ohm's law to figure out the current going through the 8 ohm resistor. So our voltage, V equals IR. Our voltage across the 8 ohm resistor is 10 volts. We're looking for current. The resistance is 8 ohms. 10 divided by, something on my shirt. 10 divided by 8, that is 1 and a fourth. Yes, 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 yes. Yes. 1 and a fourth, 1.25. I had to double check myself. Don't know why. I doubted myself there, right? 1.25 amps. All right, so that's our current that's flowing through this branch, right? So now we know the current flowing through the 6 ohm resistor, which means we can find the voltage across it, right? We have current flowing through the 6 amp resistor or 6 ohm resistor. We have the resistance of the 6 ohm resistor, so we can find voltage using Ohm's law. Ohm's law is the key to everything. You see that very clearly now, I hope. So V equals IR. We're looking for voltage. Our current is 1.25 amps. Our resistance is 6 ohms. 1.25 times 6, 1 and a fourth times 6. 7.5, I should have known that. Voltage is 7.5 volts. Again, a good double check here is that it's less than 10, right? This 6 amp, or the 6 ohm resistor can't have larger than 10 voltage if the 2 and the 6 are supposed to add together to equal 10. So that checks out. We did good maths. But yeah, that's the answer to part D, 7.5 volts. This was just to show you how you could break down both options. That's a lot of math on my whiteboard. But we're not going into this stuff just because we ran out of year. Sad. Sorry if you like this and think this is neat. But yay if you don't. But yeah, I just wanted to show you that to show you what you could do with this if you were interested in this in the future. But problem number 1 is really all that will be covered in the exit ticket for this. So that's all you really have to deal with. But yeah, that's our last circuit thing. That's our last YouTube video lesson. Again, if I might have forgotten to say this in some of the classes, but I do have something really funny that I'll post here in a week or so, I guess. I don't know how long it'll take me to dig through this and deal with the other stuff. So be on the lookout for a funny video incoming. Sorry, this one ended up being kind of long, I guess, with the challenge circuit. But hop on that exit ticket. Get caught up on work if you're behind. This has been lovely. YouTube has been a great experience. But hope to see you guys in person. Bye.